So gentlemen, we were talking about heat transfer, and that too in the case of external flows. Okay. So till this point we have been talking about flow over flat plate. You have seen few different relationships. Most of them come from experiments, right? And the important thing to remind is that this Nusselt number is a function of this X star, Randall number and Prandtl number. And if you put a bar over there that takes care of the average value, then this would vanish. Okay. Similarly, this CF would be a function of X star and what? Reynolds number only. And if you again take a bar, average value, this X star would vanish. Why? Because you differentiate it with respect to X. Okay. We talked about this thing as well, and I gave you a reading assignment on the use of liquid metals for heat transfer in different applications, and I asked you to go back and Googlify these terms. Okay, so please go back and see where you can have these liquid metals and why they are considered more effective as compared to the other common liquids in those particular applications. So anyways, we were talking about this relationship. Applicability range is quite high for this relationship, and a good thing about it is you can use it for not only isothermal surfaces, isothermal flat plates, but you can also consider this relationship for those situations where you have non-isothermal surfaces. So non-isothermal surfaces means where you can vary the temperature along the surface. Okay. So, but a very important thing which is generally, you can say, which may be generally considered in industrial applications. Why you don't go into those kind of details? When in industry you start working on some equipment, you don't go for the level of turbulence in the coming stream. You don't consider it. You just consider your incoming stream as smooth as possible. Okay. If it is air, you don't consider any kind of gust over there. So generally, in ideal environments, when you design the equipment or when you look at the performance of the system, generally they considered smooth flows. Okay, and this is a big assumption when we consider the internal flows as well. We will talk about that in the next chapter, inshallah. So this relationship, make it a star over there. This is a widely applicable relationship. Now the problem comes in when you have a plate just like an isothermal plate, right? So that relationship could be used, but I told you we talked about the error margin. I told you that the error margin could be quite high while you use that relationship. But there are certain dedicated relationships for these plates. Now what does that mean? For example, this is the plate. You can see that, and this length of the plate, the initial length of the plate, the flow is coming from this side. The initial length of this plate is, let's say, quite close to T infinity, quite close to T infinity. It means heat transfer does not occur on this portion. Okay. Now, right after this point, you have different Ts. Right after this point, you have different Ts. Now it means heat transfer would occur on this portion, the later one, isn't it? Heat transfer would occur on the later portion. So it means this plate is having unheated length. Unheated length means there is no heat transfer. So this is the unheated length, and that unheated length is being represented by this term zeta. Okay. So because friction remains the same. Friction would be all along the plate. So you can say that the velocity boundary layer would start developing from this point, start from right at the leading edge. And thermal boundary layer would start developing from this point, isn't it? Wherever you feel the difference between the temperatures, from that point onwards, thermal boundary layer would develop. Right? So thermal boundary layer would start developing from this point onwards, and velocity boundary layer would start developing from this point. Okay, so this is something which is known as unheated length. By the way, what applications you can see in your daily life if you look at these kind of problems? Just think of it. It is quite common to deal with those kind of equipment, especially in an engineering university. You keep observing these things. Might not be that common in our department, but that is common. I am just talking about the observation. That is the most common thing nowadays. Can you think of a motherboard? What do you have on the motherboard? In some portion, it is simply a flat plate, isn't it? And in the middle of that, you may be having a processor installed on it, isn't it? So if there is a processor, it is consuming some kind of power. You understand that? So it means there would be some kind of flux as well on that processor portion only. So you can say that at one side of the plate or at one side of the motherboard or the processor, there might not be any kind of heat transfer, right? But right on the processor thing where that small chip is installed, you might have some heat transfer. You understand that? So some length is unheated and some length is heated. Okay, so this can be seen as one of the applications. Now the point is how you can find out Nusselt number, the local value, and Nusselt number, the average value in this case. Look at those relationships. If the heated section is maintained at a constant temperature, T equals Ts, for x greater than zeta. Obviously for x less than zeta, the length would be unheated. Okay, so x greater than zeta, for this length, you can use these relationships for laminar and turbulent flows. And you can find out the temperature, all the fluid properties at film temperature. Okay. So these are the relationships for so these relationships, they are only dependent on Reynolds number, Prandtl number, and you can see a term zeta over there as well. Would there be any what? Conduction within the plate. Now whenever we say this is isothermal, so it means there would be no conduction. The whole surface is at the same temperature. You are talking about this thing? Okay, yes, then obviously it would be. It would be. You are talking about this, the heat transfer from this point to this point, isn't it? Right? So then it should be. But we are only interested in the convection part. Okay, obviously it would heat the other point as well. Obviously it would heat. But it depends on the thermal conductivity of this plate. You might have seen that there is a specific material used for the manufacturing of those boards, electronic boards. Right? So that might have suppressed this conduction portion so that you can carry it. Okay. So this Nusselt number is dependent on Reynolds number, Prandtl number, and the heating length. Okay. So this is the use, and these relationships are local, for local Nusselt number. So how can you find out that average Nusselt number? You can't do it analytically. Analytically it cannot be done. Okay, just look at this relationship, try to integrate it once at your home. Okay, and you would find it that this cannot be integrated analytically. So what you can do is, there is another alternate where you can integrate numerically. Just like you solve those partial differential equations numerically, you can integrate the things numerically. Okay, and Once you integrate those relationships numerically and you establish the correlations, remember these relationships, they didn't come from straight away integration. They have come from the numerical integration, and then correlations were developed using curve fitting, interpolation, and all those techniques. But anyways, in that case, this time average convection coefficient for laminar flow is, you can consider it like L, zeta over L raised to power 3 by 4, and then 1 minus zeta L. And there is a product term which is x is equal to L. It means you multiply this term with the value of h at x is equal to L. Now the point is how you can measure this one, how you can compute this one. This can be computed from these relationships. Like for example, if I ask you what is the Nusselt number at x is equal to L, you can put x is equal to L over there and give me the value of the Nusselt number at x is equal to L, right? And how you can compute h then? What? Isn't it? You can find out h at x is equal to L from this relationship, and then multiply this with this factor, okay, to find out h bar. H bar means averaged values. So similarly, these are the average values, and these relationships are true for what? Flat plates with unheated lengths. Okay, I hope you understand the use of these relationships, right? And you can see the practical application of whatever you are learning in your mathematics course. This is something where you would see what is the application of the course on numerical methodology. Okay, those curve fittings, those numerical techniques, integration, differentiation, there are so many situations because the situation becomes too complex to handle analytically. So then you have to opt for those techniques. So any question? Right. Now, if you have a uniform heat flux, all those relationships were based upon isothermal surfaces. Now, if you have a uniform heat flux, then what? You can use these relationships. Nusselt number is again dependent on some coefficient multiplied by Reynolds number raised to power m multiplied by Prandtl number raised to power n. You see, all of those relationships are of that previous form, and there are ranges of parameters where you can apply those relationships. Prandtl number 0.6 greater than 0.6, then these relationships. So any question? You can find out this q dot, the total heat transfer rate by multiplying this q dot s into as. Now q dot s would be known to you because you have a uniform heat flux on the surface. Okay, so you can find out ts from this relationship then. This is just a description of that, how to find out that ts. Okay, any question? The important conceptual point in these studies is to how to use particular relationships with particular assumptions and how to extract few parameters out of it. Okay. Now, you might have seen those figures earlier as well in fluid dynamics course, right? What kind of vortex sheet it is? Come on. You remember these vortices? Clockwise vortice in the upper row, anti-clockwise vortices in the lower row. I explained all those things during that course. Now these are bluff bodies. This is just like a top view of the building, isn't it? It can be a top view of the building as well. Now This is the cylinder. Now it can be a pipe. Just see, for example, this is the side view of a pipe, let's say right in the middle of the stream, where you are using it for transportation of some oil, or let's say some other thing. No, so if the flow stream is coming from this side, how would it behave? Now these vortices, why we need to study those vortices? It is not just to get those fascinating figures only. What is the role of these vortices? They apply forces on the structure. You might have seen those shaking of buildings and shaking of bridges, isn't it? That vibration of buildings. Okay. So what is that? That occurs due to the formation of these vortices. Okay. It is just like that. Each and every vortex, it pushes the structure and then it moves on. It gives a push to the structure and then it moves on. It means that structure would have continuously oscillating forces applied on that particular structure, okay, that building or that any pipe or anything else. So if it happens, you might have seen that famous video of that Tacoma Bridge, right, where it was horribly oscillating and then it broke. So same things happen when there is an earthquake as well. If the buildings start oscillating at their natural frequencies, obviously there would be resonance. You can understand it this way. So this topic, either you study it in your advanced fluid mechanics course if you happen to get that chance, and this can also be studied in your vibrations course as well. But anyway, you know the idea what is going on. Why? Because I have already discussed this thing in detail. So this is how this laminar boundary layer separates. You see, this is kind of the structure of the vortex. You might have seen that. I mean, it tries to rotate. And I gave you an example in a very, you can say, layman's, from layman's point of view. We discussed some examples as well. You might have seen buses and trucks going on the road, right? You might have seen some papers in their wakes, and you see they just start rotating in violently, right? So what happens is they are basically trapped in a vortex. So that's why they try to rotate. So similar things you can observe it in chimneys as well. But anyways, this is a long topic. I just want to make sure that you understand. You have already understood that. Why? Because we have discussed these things in fluid dynamics course. The only thing is you have to revise it. Okay. So I have shown you the video just to give you a reminder that we have done that earlier. Please go back, check your fluid dynamics course. Make sure you know how those vortices are developed. We have talked about those things. Okay. How the boundary layer separates, how the wake develops. Why do you use those golf balls? You remember that? We talked about the reason behind the dimples on the golf balls. Why? Because you need to reduce the drag, and by introducing those dimples on the ball, you do what? You try to keep the flow turbulent. Okay, and in case of turbulent flows, you would see that the separation point, again, just to remind you, you remember this, that we chose this thing as theta, and at this point at 80 degrees centigrade, let's say if it is an 80 degrees centigrade, so there may be separation from this point onwards, and if you keep the flow turbulent, that might separate at a higher angle, right? And as a result you have a smaller wake. Okay, and consequently due to that smaller wake you have a smaller drag. That's why you have dimples on the balls. Okay, so by this thing I just wanted to give you a reminder. You should remember this figure as well. Okay, so this figure where you draw the time average CD, this is time average CD, sorry, not the, yes, time average CD against Reynolds number. You remember we talked about in this region CD was decreased using this relationship 24 by RE. Okay, this is just like a straight line. and then after a certain Reynolds number it goes down. Why does it go down? Due to the formation of turbulent boundary layer. Okay, so what happens for turbulent boundary layers? The separation points, they move ahead to the rear portion, those flow separation points. Okay, so I would not discuss this in detail because we have done that already. The only point is you need to revise it, right? If you have any question from that particular point, you can ask it now. Otherwise you can go back, check this graph once again. Okay. So again, these are just the descriptions taken from the book about the behavior of different Reynolds number. So any question? No question? Okay. You are talking about these two plots? Yes, it is about this smooth cylinder. I'm sorry, I think yes, this is for smooth cylinder. This 24 by RE. You can see that there is a small sag in that curve, but you can consider it as if it is behaving linearly. Okay. So these are the points which gave you the same information. I picked it from the book, right? They are in the slides. You can read that. We have discussed all these things in great detail. Okay, so I don't want to revise it once again. You can read it yourself. If you have any question, you can ask me. Okay. I hope you remember this figure as well. You see, this is the separation point. This is the separation point when you have a laminar flow, and when you have a turbulent flow, that separation point has gone to the rear portion. You see, from this point onwards, so wake width has decreased. So resultantly, wake width decreases. What happens to CD? It decreases. Okay. You see, Reynolds number is 15,000 over there and Reynolds number is 30,000 over there. So let's see this one. These plots are for surface roughness. You have seen these plots earlier. Again, taken from the previous course. CD versus Reynolds number, you have those figures. Now epsilon by D is the relative roughness. You see, this depends, this epsilon is kind of the height of that roughness element. Okay, and in your instrumentation course you would learn how to find out or how to measure that roughness height. In your instrumentation course you would learn that. But my point is, if you have some roughness element height, you can find out this relative roughness. Again, you see, the trend is to find out the non-dimensional number, epsilon by D. The trend is to find out non-dimensional numbers. Now, there is a sudden drop. There is a sudden drop. Why does that drop happen? Yes, transition from laminar to turbulence. Transition from laminar to turbulence. And if roughness element is not there, you have a smooth cylinder or smooth ball. What happens is, this transition happens at larger Reynolds number. But if you make the ball rough, this transition starts happening at smaller Reynolds number. Right? So if you make the ball rough, that transition would happen at smaller Reynolds number. And that smaller Reynolds number, you can see your CD decreases to a great extent. And what is the physical reason? separation delays. Flow separation delays, and the separation point goes to the rear end of the sphere. Okay, any question? No question? Okay. So there is another interesting point which I just see and remember. Why do you see an increase in those CD values? Why do you see it? There is a drop, sure there is a drop, but then after that drop there is a slight increase in the value. You know that? Sorry? Come on, you know that. After formation of turbulent boundary layer, this drag starts increasing. Why? Come on, think about it. Okay, I would leave that question to you. I have answered it. Check your notes. So this is about the Nusselt number. We have looked at CD. Now we look at this Nusselt number. Now these are the plots. These are the plots for local Nusselt number values. You remember we described CD in terms of theta previously. Now we are describing Nusselt number in terms of theta. Till the time you talk about that flat plate, we keep talking about this Nusselt number with a subscript x. But as we move on to this cylinder thing, we represent this Nusselt number local value as nu theta. Why? Because now we are talking about angular positions. It is quite easy to describe it in those terms. So anyways, generally we would not be interested in those local values. Generally we would not be interested. We would be interested in this average value. Okay, if at some Reynolds number you need to know the local Nusselt number, you can see that plot and find that out. Again, these variations are due to the same reasons which we discussed earlier. Like for example, there is a separation point, okay, then there is turbulence boundary layer. If turbulence boundary layer is there, obviously heat transfer would increase. Okay, so there would be a sharp increase in the Nusselt number value, you see. Right? So you would feel that, you would know that this is the point where turbulent boundary layer starts formulating. Right? So if that turbulent boundary layer starts forming, it means there is an increase in heat transfer rate. Right? So if there is an increase in heat transfer rate, there would be an increase in Nusselt number. So same happens for different kind of Reynolds number. You can see this plot. So major interest would be in the value which is averaged value. Okay? And it is found at film temperature. Is there any question? Sorry? So why is it? So it is the same answer. Look at that. You are talking about this thing? You are talking about this thing? Or this thing? You are talking about this thing? So there is a question. There is a turbulence boundary layer and then it decreases. I have shown you the same kind of figure earlier. Let me see that whether it is there or not. Just a minute. Yes, this one. At the turbulent boundary layer, you have the maximum H. Then it drops. Why does it drop? Shazan, why does it drop? Come on, you know that. Yes, the temperature gradient that decreases. Due to what? Thickening of the boundary layer. As you move along the plate, that boundary layer gets thicker and thicker. Okay, so this is the same reason behind those variations. So anyway, so it drops due to thickening of the boundary layer, right? Sorry? No, even if even if this is a turbulent boundary layer, as you move along the plate or as you move along the cylinder, that boundary layer needs to be thicker. It grows, right? So anyways, for the average Nusselt number for the cross flow over a cylinder, what do you mean by cross flow? Cross flow means just like this one. This is the cross flow. Okay. One relation proposed by Churchill and Bernstein in 1977 is this one. You can use this relationship for which value? Averaged value. For local values, you can consult this plot. And all the fluid properties are measured at film temperature. For flow over a sphere, Whittaker in 1972 recommends the following comprehensive relationship, this one. Why it is a comprehensive relationship? Look at the range where you can use it. Reynolds number from low to very high, Prandtl number from low to very high, and the same is for mu infinity over mu s. Okay, so these are the relationships used for heat transfer coefficient for bluff bodies. Yes, because in nature things do not happen abruptly. Obviously there should be a decrease, continuous decrease, and then it would increase. Although that increase and decrease may happen in a very small distance, but still it needs to go down continuously. But there are few discontinuous phenomena in nature as well. It is not sinusoidal. Okay, you can see that there is a peak and then there is a trough. Okay. Sorry? You talk about this one? No, then it stays over there. Why? Because the Nusselt number is having these, you can say that the Nusselt number is only dependent on what? The temperature on the surface and the temperature which is in the free stream. CD has two components. What? Pressure and friction. So you need to take care of both of those things. You cannot see the similar patterns over there, but you can find some similar reasons for happening of few, you can say few distinct phenomena in CD and in case of Nusselt number. You can find out the similar reasons, but it does not happen all the time. Okay, any other question? Right. So if you have those kind of bodies, how you can find out these Nusselt numbers? Just look at that very carefully. If you have a cylinder, for gas or a liquid does not matter. For this range of Reynolds number, go for this one. For this range of Reynolds number, all the respective relationships are there. The only thing is you need to find out the appropriate range of Reynolds number. And in case of cylinder, what is the characteristic length? Diameter. You find out Reynolds number like this. Okay, and generally this V is what? This is the oncoming velocity. This is the velocity which is coming on to the cylinder. Okay, so you can see that. So for square, if you use a gas, this is the relationship. If you have a square which is tilted at an angle of 45 degree and the liquid is the gas, this is the Nusselt number, Reynolds number, which you can have in few different applications. You have this relationship. Okay, and all the relationships you can see that the coefficients are changed. Coefficients and those exponents are changed. Generally Prandtl number remains the same, but those exponents are changed. And those exponents are just dependent on what? The slope of that curve which you try to fit on that data. Okay. Generally for gases, because you don't use those, I think, those duct shaped pipes in those applications where you have liquids. You remember I told you the difference between the duct and the tube thing. You remember that? I told you that duct is used for what? Those refrigeration applications and those for transportation of gases only. Generally you use those ducts over there. Okay, so these are few other things as well. There are some other shapes: ellipse, vertical plate, hexagon, and hexagon simple. You can see the relationship as the same form. Okay, so you need to consult this table dependent on the system which you have, right? Now this is quite interesting. This is, you can say, this is the topic which is going to help you in finding out the performance or the heat transfer related issues in heat exchangers. Okay, you might have seen that shell and tube heat exchanger. Have you ever learned about it? So what is that shell and tube heat exchanger? That you put some tubes in a shell, and through those tubes, it means within those tubes you have, let's say, some liquid, some fluid going on, and within that shell, it means outside those tubes you have some other fluid. Okay, and you transfer the heat from one fluid to the other. Okay, so that is why it is known as heat exchanger. Why? Because within the tubes you have one fluid, outside the tubes you have some other fluid, right? So this heat basically heat transfers from one fluid to the other, and this is one application of heat exchanger. We would see few different types of heat exchangers in the next chapter or next to next chapter, inshallah, but for the time being I am just going to discuss, because we are only discussing external flows. So what happens for the temperature, as far as the temperature is concerned, what happens with that temperature profile if you consider flow over a tube bank. Tube bank means there is a bundle of tubes. Why? Because in the heat exchanger there are so many tubes, bundle of tubes, right? So those bundle of tubes, they are arranged in two patterns. One staggered. This pattern, just look at that. This pattern is kind of a staggered pattern. I hope I spelled it correctly. Staggered pattern. You see, in this line you have those cylinders, and then you have these two tubes. Then again the same pattern. So after each alternate row you have the same pattern. So this is something known as staggered pattern, and this is something which is known as inline. These are the two generic patterns used for these applications, staggered and inline. Now see that you have one fluid inside those pipes, inside those tubes, and the other fluid is flowing over them. Now you can imagine that if flow over a simple cylinder becomes too complex to handle analytically, what would happen to these kind of flows? You can't go for analytical solutions for these kind of flows. So you have to rely on experiments, or you have to rely on numerical simulations, and generally those correlations are developed. So I hope you understand the reason behind widely used correlations for these applications. Why? Because it is too complex to handle analytically, right? You cannot solve the Navier-Stokes equation. Like for example, if you start thinking about the solution of the Navier-Stokes equation for this problem, let's talk about the simpler one, this one. Can you think of the boundary conditions? I mean, you know that on this surface u would be 0, v would be 0, then velocity would be 0 on all those surfaces. Let's say you say that this is the inlet value. Okay, fine. We are going to have v infinity equals 1 meter per second. Fine. You can describe pressure over there, for example, in some case. How can you solve it? I mean, to solve this problem on a simple flat plate is very complex. How can you solve this one? So that's why you have to rely on experiments and numerical simulations. You put the data on the graph, and then you try to fit some kind of curve onto that one, and you come up with a correlation, experimental correlation. Okay. and these relationships are also known as empirical correlations. There is a word known as empirical. This is empirical correlations as well. Experimental correlation, empirical correlation. So there are two arrangements which are used for shell and tube heat exchanger. One is the staggered one, and the other one is this one, inline. Okay. We are going to discuss few points for the flow over these tubes. I am not talking about the flow inside the tube. I am just talking about the flow over these tubes, around these tubes. Okay. Just look at this figure. There are few specific parameters which are associated with these arrangements. You can see this inline arrangement. Now, this distance between those two cylinders in this horizontal arrangement is known as longitudinal pitch. This length, this distance, this gap is known as longitudinal pitch. Similarly, this vertical gap is known as transverse pitch. Okay. So S subscript L, this is the longitudinal pitch which defines the horizontal distance between the tubes, between the cylinders, and this S subscript T defines the vertical gap, vertical distance. Now, what happens is that we consider, again, look at the assumption. Just to solve this problem, look at the assumption. You say that flow is coming from this side. It would pass through these tubes and then it goes straight. We assume it. By the way, does it happen in reality? Not at all. Not at all. Because the presence of so many tubes would make the flow. There are so many eddies. Just look at the structure. This is the flow visualization. Just look at the structure. I mean, you can see very small vortices and very other flow patterns. Many complex flow patterns are there. So you can think of that. So look at the assumption which is big, right? What we can happen, what we can say is, this is the method how you define longitudinal and transverse pitch in case of inline arrangement. How can you do that for staggered arrangement? Now, obviously, this is something which is the longitudinal pitch. This is something which is transverse pitch. And then there is another pitch associated with this staggered arrangement, this one. And this is diagonal pitch. This is what? Diagonal pitch SD. So diagonal pitch SD is only associated with the staggered environment. Now see, my point is, just look at this figure. Okay, let me go to this one. These are two tubes. By the way, these lines are just considered they pass through these tubes, the center of these tubes. Now, I can say that this is what? This is ST, and just consider the outgoing length of these pipes as L, outgoing length. Okay. So what would be this area? I am just talking about this area. What would be this area? ST into, it just looks like a rectangle. It just looks like a rectangle. By the way, flow is coming from this side. Okay. Now, after passing through this region, that flow needs to go through this region. Now, what is this length? This length is what? ST minus D. So this A2 would be what? ST minus D into L. Now, in these applications, very important point, in these applications, Reynolds number is defined with the maximum velocity, not with the oncoming velocity. In these applications, Reynolds number is defined with respect to what? Maximum velocity. If I define this Reynolds number, I would say that V max, not V infinity or V incoming, multiply by diameter over nu. So the problem is we need to find out where that maximum velocity occurs. From Bernoulli equation, where should that maximum velocity occur? Where the area is minimum. If you look at that, this area right in the center of these tubes, isn't it? The area is minimum. If you go to this point, again area increases. If you go to this point, again area increases. Okay. So you can see that the minimum area, that is right in the middle of these tubes, and this is the minimum area which you can have. So what does that mean? That means maximum velocity would occur at this second section, area 2. Okay. In any case, if I just try to develop some Bernoulli expression for this flow, can I say that rho 1 V1 A1 would be equal to rho 2 V2 A2? Can I write this thing? So this is the area where the flow is coming onto it, and this is the area where it needs to pass out. So I would just consider this area as the inlet and this area as the outlet of some section. So rho 1 A1 V1, this is section 1 and this is section 2, can be written as rho 2 V2 A2. By the way, this V2 is V max by virtue of what? Okay. So what is this? Rho 1 can be cancelled. Why? Because we are just talking about incompressible flows. We consider it to be incompressible. Obviously, that's the general assumption which you can take, because the flow velocity is quite high, so it would take time to change the temperature of the fluid. It would take time. But we assume, it's an assumption, it's a big assumption, but that's happened in most of the industrial applications, that you just assume that it is going to be incompressible. Okay. So what does that mean? V1 A1, what is that A1? This is ST into L. So V max, what is that A minimum, which is A2? So this could be written as ST minus D into L. L can be cancelled. So what about V max? You can have V max as V1 over V1 ST into ST minus V. So V max is basically dependent on this transversal pitch . Okay, so this is how you find out this V max. So after finding out this V max, you would go to this calculation Reynolds number. Why? Because Nusselt number would be dependent on the Reynolds number. You have to look at the appropriate relationship, correlation. So you would find out this V max first, and then you would find out this Reynolds number. Okay. So what happens in case of staggered arrangement? This is quite interesting. Once again, flow is coming onto it. This is the area A1. Let's say this is A1 area. A1 would be equal to STL. ST is what? Transversal pitch. You remember that. Now this pitch is what? Diagonal pitch. Now I mean, the fluid has to pass through this area, and then it would have to go through this one. So the point is, which one is the minimum area? This one or this one, isn't it? The minimum value from these two areas would decide where the maximum velocity occurs. There are two areas, this area and this area. So whatever is coming in, I can just assume that it is evenly distributed into these two. So there are two cases. Case 1, this area, I would say this area A2, I would say this area is A2, and just consider this area as AD, this area. Right, this area as AD. So case 1 is A2 is less than AD. So velocity Vmax would have the same relationship, St over St minus d into V1. It would not change. It would be just similar to the previous one. So there could be case 2 where AD can be lesser than A2. Then what? Just apply that Bernoulli equation. Rho 1 V1 A1 would be equal to rho 2, I would say Vmax. I would not use the word. So the flow which is coming here, it is divided into these two portions. So there are two outlets. There are two outlets, one here and the other one is there. So Vmax AD plus rho 2 Vmax AD. Why? Because there is just one inlet and then there are two outlets. Flow would be evenly distributed. We just assume that flow would be evenly distributed in this area and in this area. Okay. So what I can write is, I can say this is 2. So rho 1 is basically equal to rho 2. I can just consider that. So in that case, V1 STL equals 2 Vmax. By the way, what is that AD? SDL. Yes, this is SDL. And how you can find out SD? Which theorem? Pythagoras theorem. Which theorem? Pythagoras theorem. So you can find out SD from this relationship. So what you can see is, in this case, Vmax would be equal to what? St over 2 SD V1. Is that the relationship? Sorry? Okay. A2 should be what? No. If you just look at this value, fine. If you just look at this value, this is the under root thing. How can you always say that? How can you say that? I mean, we are just interested in this length. This length. Sorry, this is from center to center. This is not from this is from center to center. No, I am sorry. Yes, this SD is from center to center. I am sorry for that confusion. SD is from center to center. Diagonal length. And the same is for longitudinal pitch, and the other one is from center to center. Yes. I just hold on. Let me. AD perpendicular area. Why? Because the flow is going like this, isn't it? Flow would be distributed like this. So this is the perpendicular area. No, obviously, if it travels straight, there is a hindrance. It has to pass through this area. Yes, your question. Your question. No, A2 has to be from this side. That's why I picked it as A2 is what? St minus D. So half of D comes from here and half of D comes from here. Okay. Oh yes, thank you so much. You are talking about this SD minus D term, right? And then you multiply it with L. Oh, thank you so much. Yes, I made that mistake. I am sorry for that. So let me put it this way again. Rho 1 V1 A1 equals rho 2 V max. I would use the word A min once again, and by virtue of my previous discussion I would just put the word 2 over there. So again V1 ST equals 2 V max SD minus D, right? And then V max would be equal to ST over 2 SD minus D V1. That's what the correction is. I'm sorry for that. So that is cancelled. No, I am talking about this. This is A1. This is A1. This is A1. So this is the assumption where you have A2 less than AD. There you subtracted D from ST. But if you have this assumption, this situation where AD is less than A2, then you need to, I'm sorry for that, this is wrong. This one is correct. Okay. So I hope you understand that how to find out Vmax. So the point is you find out that Vmax and then you calculate Reynolds number. Okay. So these are again the same things. Now if you have Nusselt number for flow over tube banks, if you have Nusselt number for flow over tube banks, Zhukauskas, he is the scientist, again proposed in 1987 in some journal or paper or in some of the conference presentation, he might have presented that the Nusselt number should be presented in this form for flow over tube banks, right? And C, M and N depends on Reynolds number. So I would show you the correlations over there. For inline arrangement, for this range of Prandtl number, you should use these relationships. Okay, and remember, for these relationships, fluid properties are measured at mean temperature. This is not the film temperature, this is the mean temperature. Mean temperature what? This is the inlet temperature plus exit temperature divided by 2. It means I am just talking about this inlet temperature. This is the inlet temperature. This one is the inlet temperature where the flow is coming in the shell, within the onto that bank of tube, and this is the outlet temperature, exit, right? So you would not consider this TS on the surface of the tubes. You would consider this inlet and this exit. So this is mean temperature, which you would use to calculate what? Fluid properties. Okay, remember that. Before this point we have been using the film temperature. For this correlation you have to use mean temperature. But anyways, this is the table where you can find out the relevant values of those coefficients and exponents M and N. And then there is a very interesting point. These correlations are established for longitudinal number of tubes greater than L. Longitudinal number of tubes greater than 16, right? If you have lesser than 16, then what? Then you need to introduce a factor, correction factor, which is known as F. Okay, which is known as F. So this correction factor can be found out through this table. If you have longitudinal rows, I hope you understand what is longitudinal. You can see that in the figure. Longitudinal tubes, longitudinal number of tubes, like for example, look at this one. How many longitudinal tubes are there? 1, 2, 3, 4, 5. So if you have less than 16, you have to introduce that correction, F. And for different kinds of arrangements, you can find out 0.70, 0.64 for only one tube. If you have two tubes, two rows of the tubes, you have this relationship, and similarly for this one 3. And if you, for example, 4, 5, if you want to have 6 tubes, then what? You can interpolate. Okay, so this is the data which you can use for finding out the Nusselt number of flow over tube banks. Now the point is how you can find out exit temperature. By the way, this is a very interesting point. How you can find out the exit temperature. Let's say not the exit temperature, let me put it this way, that if you want to find out heat transfer rate, we have found out Nusselt number, you can find out H. If you want to find out heat transfer rate, what you can do? You can simply use the Newton's law of cooling. You can multiply delta T with H, right? But the point is, what should be delta T? What should be delta T? There are two approaches. This delta T can be this one. Delta T is equal to Ts minus T average. What is this T average? This is Ti plus Te divided by 2. This can be delta T, but this delta T value basically gives you wrong results. I would use the word over predicts. It over predicts the heat transfer rate value. So what is the alternative? You go for log mean temperature difference. It is represented as delta T subscript Lm. So this is the log mean temperature difference which you should use to find out heat transfer rate in case of convection for flow over tube banks. You should not use this one. Okay, and very interestingly, this T exit is found out to be this thing. How? I would prove it in the next chapter. Once we talk about the internal flows, I would prove it in the next chapter, but for the time being, just take it as it is. T exit. Now you can know the temperature T inlet, isn't it? Why? Because it is something which is given, which is known. How you can find out T exit? So T exit can be found out by this expression. How you come up with this expression? There is a proof in the next chapter. We will do that inshallah. So T exit equals Ts minus Ti exponent. This is e raised to power minus ASH over m dot Cp. M dot is the mass flow rate, As is the surface area. I mean, so what should be the surface area? The surface area, if you have surface area for one tube, you need to multiply it with the total number of tubes. If you have, let's say, 20 tubes in some heat exchanger, you need to multiply one surface area with total number of tubes. So this is something which needs to take care of. So the same point, you can find out this Q dot using this log mean temperature difference. Okay, so there is a small point about pressure drop. Obviously, if there are tubes, there would be hindrance in the path of the flow. Okay. Anyways, we were talking about this pressure drop. So pressure drop, it is a measure of the resistance offered by the tube bank in the flow for the flow, against the flow. Okay. So just like the friction plays its role in putting the resistance when you have a pipe flow. You remember that? If you consider a smooth pipe, there is no friction at all, you don't need to have any kind of pressure drop, isn't it? Right? So that pressure drop or that pumping power is associated with the resistance offered by the pipe or the vessel to the flow. So how you can find out this delta P over there? Just see, this is the relationship which you can use for finding out the pressure drop for flow over tube banks. This is NL, longitudinal number of tubes, Then this is a correction factor F. Sorry, this is the friction factor F. By the way, this friction factor is not equal to CF. You remember that we talked about two types of friction factor. Darcy friction factor, and what was the other one? Come on, go back and check. Okay, Darcy friction factor, and there is another one. I would not give you its name. Just check it yourself. So, but this is the other friction factor, which I am not going to name. You should check it from your notes. And this X kind of thing, this is a correction factor. So rho V max over 2. Rho V max square over 2. So this is the value which you should find out for delta P. Now the point is how you can find out this friction factor F. This is the plot. And there are two plots for inline arrangement and staggered arrangement. There are two plots for inline arrangement and staggered arrangement. Just look at these parameters. You can look at these parameters, find out the appropriate curve, find out the appropriate friction value against some Reynolds number and put it over there. There is another plot for this correction factor zeta. Zeta, or you can say, just to make it simple, this is X. Right? So similarly for staggered arrangement you have this plot, and these plots are used to define what? F and zeta. Okay, and to find out the appropriate curve you need to find this one, PT. This PT is already defined over there. Okay, now you need to find out this pressure drop. Why? Because you need to find out the pumping power, isn't it? You need to find out that pressure drop. Why? Because you need to find out this pumping power. So that pumping power would be equal to this relationship, where this volumetric flow rate is equal to V, velocity, multiplied by area. Okay, so this is the area which you should cater for. So if you multiply this volumetric flow rate with the pressure drop, you should come up with the required pumping power. So that's how you can measure, or you can at least estimate pumping power or the specifications for any pump required for a certain application in shell and tube heat exchanger, or at least for flow over tube bank. So just to give you an idea, that was an example which I put it over there on the slides. Everything is there. I have already told you that before solving anything or before going for finding out the Reynolds number, first of all find out Vmax. This is the first step. Okay, just look for Vmax, find out the Reynolds number, find out Prandtl number, go to the appropriate relationship, look at the tables to find out Nusselt number. Okay, and from that Nusselt number you can go to the heat transfer rate, right, and then you can find out the pressure drop, and then you can find out the pumping power. Okay, you just need to go to the appropriate relationship and appropriate table. Every other conceptual thing has been discussed. Any question? No question?
Can you tell me about the end?
Transverse, number of rows in the transverse direction, number of rows in the longitudinal direction. Okay, so that's all about this chapter. We will talk about internal flows from next week onwards, inshallah.